this video, we are focusing on using solver add-in of Excel to solve a linear programming problem. As the example, I'm taking the ready-mix problem from the OR book of Hamdi A. Taha. So in this example, we are asked to find the optimal production of exterior and interior paint to maximize the daily profit. So the data are given in the table format and in this paragraph as well. So exterior paint and interior paints are the two products, and to produce those two products, they need M1 and M2 raw materials. So availability of raw materials are listed in here, and the total profit for interior and exterior paints are given in here. So these units are in tons and the unit of these profits are in $1,000. A market survey indicates that the daily demand for interior paint cannot exceed that the exterior paint by more than 1 ton, which means that is also one constraint apart from these two about the raw material. And here these are the maximum daily demand for interior paint is 2 tons, which means I have four constraints in this problem regarding the material availability and two regarding the demand of interior and exterior paint. So the decision variables should be exterior paint and interior paint because the ready mix force to determine the optimum product mix of the interior and exterior paints that maximize the total daily profit. So after recognizing the decision variables, I can define two cells or using those names, exterior and interior. So which we are going to find answer or assign values for these uh, cases. So I may need the unit profits to determine the total daily profit. So I name this cell using unit profit. So these are the two cells. So it is better to mark those things in a different color. At the same time, it's better to name those two cells, so that cell range using a proper name. So then if we are using formulas later without marking those cell range, I can mention the name, so automatically the range will be added. We have assigned that here. So it is now I have defined these two as unit profits. So 5 and 4 are given as unit profit for exterior and interior respectively. So now I can go to the constraints. So there I have raw material M1, raw material M2, and the demand of interior paints, and the demand exceeds, or the difference of two demands of interior and exterior. So I can write down those things under these four cells. So I wrote those things in here. For raw material M1 it is 6 4, M2 it is 1 2. For demand exceed, which means the interior minus the difference between the exterior and interior, which means exterior minus interior, and demand for interior. So interior is only here. So I'm highlighting it using another color for my convenience. And now I have to enter the right hand side values of these. So this means resource availability, and at the calculation I need to give these constraints to solver. So I need resource used column as well, and these four cells are used to indicate the direction of constraints. Let's fill those fields. So resource used are calculated during the optimization process, so I don't know those values. I can assign zeros at the beginning or wait till the last. So resource availability means right hand side value. So it is 24, 6, and here the demand is 1 ton, or the difference should not exceed 1 ton, and the demand for interior is maximum 2 tons. So I'm highlighting those cells with the same color, and at the same time I'm defining a name for those for range, so as resource availability, and I'm defining another name here, resource used. So actually those cases is my calculation when I'm feeding data to the dialog boxes. Now I need to define two cells to my uh, decision. So production is my decision. How, what is the numbers for these two cells? So we don't know it at the beginning. So I'm using 0 and 0, and we have to maximize the profit. So this cell also we don't know the value at that time, so it's better to name it using define names, and here, and we have to name the production as well. So this range is production. Now we have assigned those things, but now, so now we have defined those fields as per the question, and resource use will depend on, or is depending on the production decision. So we have to get the summation of this with this and this with this after multiplying these corresponding cells. So I'm using the sum product function to define these cell outputs. So sum product will give the sum multiplication. First multiply two arrays or two or more arrays and give the summation of the corresponding elements. My first array is 6 and 4, and I need to multiply those things, use this production values. So you can see once you define the cell range, it will indicate the name of this. So I have to define these four cells using the sum product, which means the product of these two cells and these two cells, and get the summation for this one as well, this row and this row, for this row and this row. Let's fill those things. So we have defined those four cells using the sum product function, and for this the profit depends on the production and the unit profit. So it is also sum product function which provides us the ability to calculate the total profit. So defining that cell using sum product. So now you can see by changing these two values, the total profit is changed like this, and you can do trial and error to find the profit. So here it is somewhat hard, so we set these numbers to 0 and we are going to solver. So here you have to fill these arrays correctly. Objective is to maximize the profit, so give that objective cell to here, is to maximize, so it is given by default by changing the variable cells in the production. So we have to change the production. So these two cells should be containing the decision and subjected to constraints. So what are the constraints? So this is the set of constraints. So which means resource use should not exceed the resource available column or numbers in the resource available. So first we have to give resource use should be less than or equal to resource availability. So that is my constraint, and this is automatically or by default it is stick. So keep it as it is. GR is in nonlinearity. So if you use this, you will get a local optimal number, but we need to get a global optimal number. So we are going to using this simplex LP and hit solve. Now you will see if the solution is feasible and optimal. Solver found a solution will be displayed in this result sheet, and you can get answer, sensitivity report, and the limits of the answer. So which means here you can see by producing 2.66 interior paints and 1.66 2.66 tons of exterior and 1.66 tons of interior will give the maximum profit of 20,000 for this company. And you can see these resources are fully used, but these two resources are not fully used. There is a excess of these uh, resources at the end of the day. So this is the optimal and feasible solution. Since we have the solution, we are going to uh, look at the post-optimality analysis, which means the sensitivity analysis. You can select the sensitivity report and press OK, since these are the solutions for our optimization problem or for this linear programming. And once you hit that one, you can see the separate in a separate worksheet the results is shown. So here you can see two uh, tables: reduce cost and shadow price. Reduce cost tell us how much units that we can change the objective function coefficients without changing the optimal solution we obtain using these constraints. So here you can see it is 0, which means we can't change the objective function coefficients or the unit profits of this interior and exterior by any number without changing the optimal solution, which means 20,000. So that's why it is 0. These allowable increase and decrease says, so these are the objective function, existing objective coefficients. Uh, so suppose it is 1 here. So then you can use this allowable increase and decrease. So without a number here, you can't interpret this allowable increase and decrease. So which means according to this output, we can't change 504 to any other number without changing the optimal solution that we have already obtained through this maximization. Now we go to the constraints label. So it shows the shadow price. Shadow price is the change in the optimal solution. So it can be an increase or a decrease if we change the right hand side value of a certain constraint. So here shadow prices are 0 for first constraint and the fourth constraint, which means if we change the right hand side values of those constraints, we can't expect a change in the objective function. But in here, for the second constraint and the third constraint, we have shadow prices. So which means this shadow price says if I increase the right hand side of the second constraint by 1, the objective function or the is same now. So the total profit, optimal profit, is increased by 3 points or 3 units. If I decrease the right hand side by 1 unit, the solution will be decreased by 3 units. Let's see whether it is okay. So now it is 6. I'm changing it to 5 and I'm going to solver and ask for the answer. So you can see initially it was 20, now it is 17, which means by decreasing the right hand side value by 1 unit, the total profit has decreased by 3 units. So it is clearly stated under this shadow price column. So this shadow price valid only for this range, which means the global increase is zero point 0.4, which 6 plus zero point 0.4 is the maximum limit for the increment. So it is 6.4, the upper limit. And the lower limit of the interval is 6 minus 5. It is 1, which means if we change the right hand side value of this coefficient between to any number between 1 and 6.4, we can expect a change in the total profit. So if we do that change by 1 unit, the optimal solution will be changed by 3 units. So this 3 is valid only for the whole numbers between 1 and 6.4. So you can interpret that the same thing for this demand excess constraint as well. So that is how we can perform uh, a sensitivity analysis using the solver, and this is how you can solve a linear programming problem using solver add-in.